Bismillah ar-Rahman ar-Rahim. Today we have very interesting subject. It's called trigonometric integrals. Okay, so what is trigonometric integrals? We will treat classes of functions of the following shape. So try to integrate classes of functions that involve some trigonometric functions. Specifically, we will treat this case. For example, here we have sine to the m of x cosine to the n of x dx. How to integrate such type of functions for different cases m and n. Another shape of or another class of functions we will see if we have tangent function to the power, let us say m of x secant to the power n of x dx. How to integrate such type of integrals with different, as we said, different cases for m and n. Similarly, we have the combination of cotangent of to the power m of x multiplied by cosecant to the power n of x dx. The question is how to integrate these classes of functions. How to integrate the sine-cosine, tangent-secant, cosecant, cotangent functions. We will have a nice strategy to integrate each one of these. So we will start case by case. The first case we will see here how to integrate. So this is case number one. Let me call this one case number one. Case number one, we will talk about the following case, which is, I'm listing there, we have the integral of sine to the power, what? M of x cosine to the power n of x dx. And we discussed two different cases or three different cases here. The first one of them, let me call it part A. What happened if the power of cosine is, the cosine function is an odd number, is odd. Let me say simply is odd. So what happened if the cosine is odd, or the cosine function has an odd power? In this case, I'm assuming that this number n is odd. If this is odd, I don't care about m. It could be integer, it could be positive, it could be negative, it could be rational, anything in real line. Okay. What should we do in that case? If the cosine is odd, let us imagine what will happen here. See now, if the cosine function has an odd power, look, if the cosine function has an odd power, what happened if we save one cosine function here at the end? If we just write here cosine of x, then what is remaining here will be cosine to what? To an even power here. This is even of x. Why? Because if this is odd and you are subtracting 1, that's it, we are separating cosine to the power 1. So the remaining part will be cosine raised to an even power. Then what should we do? We will use this identity. See, we have sine squared of x plus cosine squared of x is equal to what? Is equal to 1. So if we have an even power of cosine, I can rewrite it in terms of the sine function. So what do we have at the end? We have the integral involving function of the sine of x multiplied by cosine of x, the one we saved, multiplied by dx. So simply what you need to do to make this is equal to u, so we have function of u multiplied by du. And that will be done in the following exercise. I have two examples here. The first one says, example, says find the integral of, and simply I will start with a simple one, that is cosine cubed of x dx. Now, how to integrate cosine cubed? How to integrate an integral that involves odd power of cosine? That's our target now. So let's call this integral I. The strategy says, if you need to integrate combination of sine cosine where the power of cosine is odd, the first step you need to do to save one cosine function. So what I will do here, I will separate one cosine function. So what do we have? I will have clearly cosine squared of x. That is, after separating cosine of x and I have an odd power, the remaining term here will be a cosine function raised to an even power, as we said. Now, the next step. So what we did here, we just separated cosine of x. What is the next step now? Whatever I get here as an even power of cosine, I can rewrite it in terms of sine. What's happening? If we do this, we will get the following shape of the integral. Look, I'll come to the integral now, and I will rewrite cosine squared as 1 minus sine squared of x. I'm using the Pythagorean law, that trigonometric identity, sine squared plus cosine squared equal to 1. So cosine squared is 1 minus sine squared. Of course, multiplied by cosine of x, the one we saved, multiplied by the x. Now, the only thing you need to do as the next step to let u equal to the sine function. In that case, you will get du to be equal to what? The derivative of sine, that is cosine of x, of course, multiplied by the x to get the differential du. Fine. Let's go back and substitute and see what will happen now. So this implies our integral I is equal to the integral of, this will be 1 minus u squared all multiplied by du. That is cosine x dx. That's du. You see now, we are converting a trigonometric integral into a polynomial integral, which is straightforward to be done. So what is the answer for this? It is just u minus u cubed over 3 plus a constant c. Now, what is u? U, we make it equal to sine, so we substitute for it. It will be sine of x minus sine cubed of x divided by 3 plus a constant of integration c. Okay, let us see another exercise where the power of cosine is odd, but the sine function is also appearing there. So let's call it part B of this case, or let's say example number 2 of this case. So this is another exercise, says find the integral of, I will take here sine to the power 1/2 of x, and I will take here cosine to the power 5 of x dx. Okay? Interesting. We have combination of sine cosine, and we are classifying here as the power of cosine is odd. Fine. If the power of cosine is odd, the strategy says you need to save one cosine. So that's the first step. I will say here sine to the power 1/2 of x. Then I have here cosine to the power 4 of x multiplied by cosine of x dx. After separating cosine, the odd power will be an even power. So we have an even power of cosine. What is next? I need to rewrite this in terms of the sine function. So I have sine to the power 1/2 of x. What is cosine to the power 4? Cosine to the power 4 is cosine squared of x all squared. That is cosine to the power 4. Now, what is cosine squared? It is 1 minus sine squared of x all squared to get cosine to the power 4. Again, 1 minus sine squared is cosine squared. Cosine to the power 4 is cosine squared all squared. I'm replacing cosine squared by 1 minus sine squared all to get y to the power, cosine to the power 4. I need it all squared. Of course, multiplied by cosine of x dx. Now, what is next? We said the first step, we separate one cosine. Second step, I need to write everything here in terms of sine. We are done with that. The next one, I need to make a substitution now. What is the substitution? Make u equal to the sine, and that will give you du is equal to cosine of x dx. So what should we do now? We just substitute to get the following shape of the integral now. It will be just sine to the power 1/2. That is u to the power 1/2. Multiplied by, this is 1 minus u squared all squared, and cosine x dx, the one we saved, is just du. Now you see, now we convert a trigonometric integral into a simple integral. We are getting much easier integral now. So what is it equal to? This implies I is equal to. Now let us simplify, then integrate. I have u to the power 1/2, that is the item outside here, multiplied by. Now 1 minus u squared, all squared. I will expand it to get 1 minus twice the first, the second, that is minus 2u squared, plus the second one squared, that is u to the power 4 times du. Then the next one is just multiplying by u to the power 1/2. You get here u to the power 1/2 minus 2 u to the power 2 plus 1/2, that is 5 over 2 plus 4 plus 1/2, so that is u to the power 9 over 2 du. I'm integrating this with respect to u to get the following. Now it is simple one, it's just the power rule. You just add 1 divided by the new exponent to get u to the power 1/2 plus 1, that is 3 over 2 times 2 over 3. Actually, we are dividing by 3 over 2, so we are multiplying by 2 over 3. Minus, okay, I have here u to the power, I will add 1, so it will be 7 over 2 times 2 over 7, so that is 4 over 7 to the power 7 over 2. Fine. Plus, the next one, it is adding 1, so it will be 11 over 2 times 2 over 11, so that's 2 over 11 u to the power 11 over 2, of course, plus a constant of integration. And then at the end of the day, we just go back and substitute for u by sine of x to get the final answer, which is equal to 2 over 3 sine to the power 3 over 2 of x minus 4 over 7, that is sine to the power 7 over 2 of x, of course, plus 2 over 11, and that is sine to the power 11 over 2 of x plus a constant of integration c. So these two examples illustrate for us how to integrate combination of sine cosine where the cosine has an odd power. I summarize. First, we separate one cosine, then we write that term in terms of the sine for the remaining term as a function of the sine function only, and then we make the substitution u equal to the sine, du will be the one we saved, which is cosine, then it will be a simpler integral. Another time, we have sine cosine, the cosine has its own power, we separated one cosine, we wrote the rest of the thing to be in terms of sine, then we make the substitution, it became a simple integral, we integrate, we substitute back for the sine function. That is the first case where the cosine has an odd power. What happened if the sine has an odd power? That is the next one. Okay, let's go back to the first case and discuss the second part of it. We have the first case says I'm integrating combination of sine and cosine. In the previous case, we discussed if the cosine has an odd power. Now, let's remove this one and discuss what happened if the sine has an odd power. Okay? What happened if the power of sine is odd? What do you need to do? You come to the case you have here. You have the sine has an odd power, that is m of x dx, where m is odd here, multiplied by cosine, in that case n of x. We don't care about n dx. We will do exactly the same. But whatever we did for the cosine, we will do it for the sine. So what should we do? If this is odd, then saving one sine function will let the power to be even. So we have sine to an even power here times x. And if it is even, then I can rewrite it in terms of cosine. And if you wrote everything in terms of cosine, next you need to let u to be what? Cosine of x, du will be what? Du will be equal to minus sine of x dx, and you already have saved this, sine x dx. So the only thing we are left with a minus sign that can be easily adjusted, so the integral also will be simpler. Let us see an example and see how it moves, okay? I will take this specific exercise here to explain the strategy that will be used to solve questions of this type where the sine has an odd power, and this is a specific one. We have here sine to the power 5 of x, and we can take cosine to be like squared of x dx as an example. Okay, let us see how we solve this exercise, how to apply the strategy here. First, we classify them that this is an odd power, so the strategy says if you have this case, always you can do the following. You can separate one sine function, so this will be sine to the power 4 of x. This is cosine squared of x. You are saving 1 sine of x dx to the end, okay? We leave this one to the end because we need it in the differential of du, differential of u. So this is cosine squared multiplied by sine to the power 4. It is an odd. When we separated one sine, it became even power. So what should we do now? We need to integrate by using the identity. We convert this one first into cosine. What is sine to the power 4? It is sine squared of x all squared. That's one thing. Of course, I have here cosine squared of x. I am saving sine of x dx to the end. Okay? My target now in the second step to rewrite this in terms of cosine. And that will be done in the next line here. Okay. Now let us see how to rewrite sine squared. Sine squared equal to what? We have sine squared plus cosine squared equal to 1. So sine squared equal to what? 1 minus cosine squared. Fine. So this is equal to, the integral is equal to the integral of, what is sine squared? It is nothing but 1 minus cosine squared of x all squared. That is sine to the power 4. Multiplied by cosine squared, we said we will leave this one to the end. That is sine x dx. We leave it to the end. Fine. What is next? After we make this simplification here of the question, after we separate sine of x and we wrote sine squared as 1 minus cosine squared, we are ready to make the substitution now. So the next item will be just to let u equal to what? Equal to cosine of x. What is du in that case? Du will be minus sine of x dx. So it is ready. We have it here, sine x dx. The only thing we are in need of a minus sign. So this implies our integral now is equal to minus integral of what? 1 minus cosine squared, that is 1 minus u squared, of course all squared, multiplied by cosine squared, that is u squared, and we need sine x dx, that is minus du. So I'm putting the minus sign here because sine x dx is minus du, Okay, fine. Now, the rest, I guess, is simple for you. Just integrate this one by expanding first, multiplying by u squared, and then integrate. So what do we have here? We have 1 minus 2u squared plus u to the power 4. I'm just using the expansion of this, multiplied by u squared, multiplied by du. Fine. So this is equal to minus. I keep the minus sign outside. And we have here u squared minus 2 u to the power 4 plus u to the power 6. I'm adding exponents in multiplication. All of this should be integrated with respect to u, and then that will give us the answer. Now it is so simple. It became polynomial function. Integral of polynomial function is so simple. So this is minus. And I open a bracket like this. So what is the integral of u squared? That is u cubed over 3 minus 2. That is u to the power 5 over 5. Okay? And finally, I have plus u to the 7 over 7. Of course, I need to add at the end constant of integration. Okay, that's the integral with respect to u. I need to go back and replace u by cosine of x, and that will give me the final answer. Okay, so let us see this. So our integral at the end is equal to, I need to just substitute back for the u. So this is minus, I have here, and then I multiply. This is u cubed, u is equal to cosine. So that is cosine cubed of x over 3. And then we have here minus 2 over 5, if you like. And that is cosine to the power 5 of x. And then finally we have plus, we have cosine to the power 7 of x divided by 7. All of this plus constant of integration. So that is how to integrate the sine, cosine, if the sine function has an odd power. So it goes parallel to the cosine case. We The first case we separate one cosine, here we separate one sine. The two cases are almost the same. The next one, what happened if the power of sine is even? Power of cosine is even. How to treat these cases? That will be done in the next case. Now let us see what will happen if we have the power of sine, power of cosine are even. Okay, what should we do? I will say simply what you need to do is just to recall these identities. Recall this. Recall these identities. We have always sine squared of x, which is what we call half angle identity. It says sine squared of x is 1 minus cosine 2x divided by 2. And we have cosine squared of x, it is equal to 1 plus cosine of 2x divided by 2. These two identities can be gained from the double angle identity for cosine 2x. We have cosine 2x is equal to cosine square minus sine square. It is 2 cosine square minus 1, 1 minus 2 sine square. Two of them will give us sine square equal to 1 minus cosine 2x over 2, and cosine square is equal to 1 plus cosine 2x over 2. You can see this one from the following identity, that is cosine 2x is equal to 1 minus 2 sine squared of x. And you can see this one from the identity that says cosine 2x is equal to 2 cosine squared of x minus 1. Solving for cosine square and sine square, you exactly get the two identities which can be used now to solve sine to the power even or cosine to an even power. How to use these identities to solve? We'll see. An example here to apply the strategy says we have to integrate sine to the power 4. How to integrate sine to the power 4 using the half angle identity there? I need to write this one as sine what? Squared of x all squared dx. Fine. Sine squared all squared. Now we come to the sine square and we use the identity 1 minus cosine 2x over 2. So let us keep this one in front of us and apply it now. Let's use it to simplify things. So what do we get here if we simplify by substituting for the half angle identity? I have here sine squared, that is 1 minus cosine of 2x divided by 2. All of this squared dx. Okay, fine. What is next? Look here. I have 2 squared, that is 1 over 4. I can take it outside if I like, so I will choose to take it outside. Then I have 1 minus cosine 2x all squared, that is 1 minus twice the first the second, so that is 2 cosine of 2x, okay, plus next I have cosine squared of 2x, okay, squaring the second one. All of this should be integrated with respect to x, so that is dx. Fine. Two of them are easy to be integrated, the first and the second one. The third one, I have integral of cosine to an even power. Again, I will use these two identities to simplify. What do we get? We will get the following. It is 1 over 4 times the integral of, look, I have 1 minus 2 cosine of 2x plus, what is this? Cosine squared. Using the identity we have, it is 1 plus cosine, now double angle. I have 2x here, so this will be what? This will be 4x, twice 2x, all divided by 2. And I don't forget that everything here inside the integral will be integrated with respect to x. Let us simplify more and then get the answer. Look, I have 1 over 4 times the integral of. I have 1 plus 1 half, that is 3 over 2, minus 2 cosine of 2x plus I have here 1/2 of cosine of 4x. That's it. Integrate this one with respect to x to get the final answer. So let us integrate now to get the final answer now. What we did actually, we are transferring sine to the power 4 into some elementary functions like cosine only. So what is the final answer? It is 1/4 times the following terms. That will give me 3/2 times x. What is the integral of cosine 2x times 2? That is nothing but sine of 2x direct. Okay. And what is the integral of cosine 4x? It is 1/4. So this will give me plus 1/8 sine of 4x. And finally, I need to add a constant of integration. Of course, you can multiply by 4 to get the final answer. If you like in another form, just multiplying by 1/4 to get another shape of the final answer. And that will give me what? That will give me the following. This is equal to, if you like, this is equal to, now 3/2 times 1/4, that is 3/8 times x, minus, now we have 1/4 times this, so it is minus 1/4, that is sine of 2x, if you like. This is the next term. The last term we have 1/4 plus, times 1/8 is plus 1/32, and that is sine of 4x. Everything here should be added to a constant, arbitrary constant of integration. This is one example about even power of sine, even power of cosine. Of course, here only the sine function is appearing, but in between also we have the even power of cosine. So both functions appearing in the equation, and we, as you can see, apply only the half angle identity twice in order to simplify, get the answer. Now let us see both of them appearing with even powers. So let us take this specific one here. I have another exercise that says evaluate or find the integral of the following. Here we have sine squared of x, and we have here cosine to the power 4 of x dx. Let us see how to integrate such type of functions where we have sine with even power, cosine with even power. Okay, we have different ways to move actually in this exercise. I will mention 2 of them. Sine squared, cosine to the 4. I mean, different ways to move, but at the end of the day, I mean, you get the answer. You get the maybe different shape of the answer, but it is correct. Both answers will be correct. If you start applying the half angle identity, here you get 1 minus cosine 2x/2. And here you need to write it as cosine squared all squared. So cosine squared is 1 plus cosine 2x/2 all squared. Then you need to expand, multiply, simplify, get the answer. That is one way to move. Another way to move, which I will present now, is the following. I will write this one as, look, I will write it as sine squared of x, cosine squared of x, cosine squared of x. I will try to do some simplification before I move. That's my idea. So what do we have here? I will have this, look, sine squared, cosine squared. I will write it as, look, sine of x, it's very beautiful here, cosine of x, all what? Squared, multiplied by cosine squared of x dx. Until now, I did not use the half angle identity. What I will try to use here is the double angle identity for the sine. So I will multiply by 2 here to make it 2 sine cosine. If I multiply it by 2 here, it is 2 squared, so I need to divide by 4 outside. So I multiplied by 4 actually, and I divide by 4, so I did nothing here. Fine. Look, the following will be interesting now. Look, 2 sine cosine, that is sine 2x. So what we have is sine squared of 2x. That's the first one. And the second one is cosine squared of x dx. What is next? Again, I will use half angle identity now. I have sine squared, cosine squared. So what should we do now? This is equal to 1/4 integral of Now what is sine squared of 2x? It is 1 minus cosine of 2x divided by how much? Divided by 2. And what about the second one? The second one we have is, now look, cosine square. What is cosine square? It is 1 plus cosine. Okay, here we have sine square of 2x. When we use double angle identity, this will be what? This will be 4, isn't it? Because I'm taking double angle identity of sine 2x here. So double angle identity of 2x will be 4x. And the next one will be 1 plus cosine 2x divided by 2. Fine. This is multiplied by dx, and we have 1 over 4 outside. I have 1 over 2. I have 1 over 2. That's 1 over 4. I will take it outside. So that is equal to 1 over 16 integral of, what do we have here? Look, I have 1 by 1, that is 1. I have 1 by cosine 2x, that is plus cosine of 2x. Okay, interesting. And then I have minus cosine 4x by 1, so that is minus cosine of 4x. Do it this way, all the way. This is inside the cosine, this is inside the cosine, and so on. And finally, what do we have is interesting. I have minus times plus, that is minus. I have cosine 4x, okay, multiplied by cosine of what? 2x. Cosine 4x multiplied by cosine of 2x. Of course, I integrate everything here, everything with respect to x. Look here, we have 4 terms. The first one easy to be integrated. The second one easy to be integrated. The third one easy to be integrated. But the last one is so interesting. I have cosine 4x, cosine 2x. How to simplify it? How to integrate cosine, cosine, or sine, sine, or cosine, sine. I will just remind you of this, then I will proceed in the solution. I will just say, recall the following identities. That will be very interesting and very, very helpful to find answers whenever we have cosine, cosine, sine, sine, cosine, sine, with different angles, different arguments here. Okay, what are these identities? Remember this. If you have cosine of alpha, cosine of beta, always you can write this one as 1/2 times cosine of alpha minus beta, okay, plus cosine of alpha plus beta. This is something we have done in previous courses, in algebra course. What else we have? We have sine alpha, sine of beta. You can always write this one as 1/2 times what? Again, it is cosine alpha minus beta, but in this case we have minus what? Cosine alpha plus beta. Interesting. The last one we usually see in trigonometric integrals is this. If we have sine alpha, cosine of beta, then this is equal to 1/2 times, it is sine of alpha minus beta, plus sine of alpha plus beta. Interesting. Always these 3 identities are important to solve these kind of integrals where we have a combination of cosines, sines, sine, cosine. So you can use these identities. Now let us go back and continue our solution of the previous example. What we faced at the end of this example when we substituted by the half angle identities here, we end up with 4 terms. Look, we said this is easy to be integrated, this is easy to be integrated, this is easy to be integrated, but looking here we have cosine 4x, cosine 2x, 2 different angles. So I need to use this identity to simplify. I will use 1/2 cosine the difference plus cosine the sum. Let us do that before we integrate. So what is the next item here? This implies our integral I will be equal to integral of. We don't forget the constant outside, that is 1/16. So I will write here 1 over 16. Then I have 1 plus what? Cosine of 2x, right? This is the second term. And minus cosine 4x, we have minus cosine of 4x. I have it like this, okay? Then I will use the identity now. I have minus cosine 4x, cosine 2x. Using this identity, so I need 1/2 times cosine 4x 2x, so that is cosine 4x minus 2x, that is 2x, plus cosine the sum, 4x plus 2x, that is cosine 6x. So I will use that one here. So I have a minus sign, all of this minus, so I'm applying the formula now we have in front of us, so that will be 1/2 times the following. 1/2 times cosine, the difference, I have 4x minus 2x, that is 2x, what? Plus cosine of what? 6x, and again, I integrate everything here inside with respect to x, so that is dx. Everything is fine now. You are at the last stage of the solution, so this is 1 over 16. Now integrating 1, let us simplify again. We have cosine 2x minus 1/2 cosine 2x, so that is plus 1/2 cosine of 2x. Okay, this is the first one. I have minus cosine 4x, so I leave it for the time being, minus cosine 4x. Then I have minus 1/2 cosine of 6x. Okay, dx, of course, I'm integrating everything inside with respect to x. We are ready to find the final answer now. You see, beautiful exercise that combine many things. We have power of sine, power of cosine are even. Okay, we simplified first. Then we use half angle identities. Then we get some combinations where we need to use such identities to simplify. And finally now we get the answer, which is equal to what? This is equal to 1 over 16 multiplied by integrating. This will give me x. That will give me plus 1 over 4 sine of 2x. Okay? And the next one will give me minus 1 over 4 sine of 4x. And finally, I have here minus 1 over 12, that is sine of 6x plus a constant of integration, of course, c. That's the end of the solution. So this is the final answer. Of course, you can multiply by 1 over 16 inside to get another form of the solution. I will summarize the steps we have in this exercise. I have sine squared cosine to the power 4. What I did, I separated cosine squared so that I can use the double angle identity here. So I combine these two things as sine cosine all squared. I multiplied by 2, so I multiplied actually by 4, so I divided by 4. And I leave this one as cosine squared. Then I combine these two things as to be double angle identity, sine 2x all squared, cosine squared. I'm ready now to use half angle identities. I use them. I multiplied everything. I get so simple integrals here, but combination of cosine, cosine. Then I use this identity to write it as the next form, and then I integrate to get the final answer. So that is this end of the discussion when we have combination of sine, cosine. So we did cosine has an odd power, sine has an odd power, cosine and sine have even powers. What is next? The next one will be combination of tangent and secant. We will see also different cases. Now, the second combination we will treat now is the following. If we have tangent, secant, we will discuss two cases now. The first one, what happened if the power of secant is even? This has an even power. Secant has an even power. What is the strategy here? I will just sketch it here. It says, okay, if you have tangent, we don't care about the power of tangent. Now we are concentrating in the power of secant. If the secant has an even power, then what happened if we separate secant squared of x dx? If we save secant square, what will be the power here? If you have an even power and you take two of them, still you have what? Still you have an even power of secant. So what we do, usually we separate secant squared, keeping in mind that the secant has an even power, and after separating secant square, then we have also an even power. Why we are doing that? We are shooting to make the substitution u equal to tangent. And if u is equal to tangent, what is the derivative of tangent? It is secant squared. Now, let us see if we can do that. If we have an even power of secant, the question, can we convert everything here in terms of tangent? So, if we convert this one in terms of tangent and we make the substitution u equal to tangent, then this will be du. And hopefully we get a simpler integral. Let us see this. If this is even, then I can use the identity that says secant squared of x is equal to what? It's equal to 1 plus what? Tangent squared of x. So I will use this identity to convert an even power of secant in terms of what? In terms of tangent. If we succeed to do this, then what I will have at the end is function of tangent multiplied by secant square. Simply, we make u equal to tangent, and du will be secant square dx. Let us see how to apply this one in the following exercise. So I'm discussing now power of secant is even. So I will choose a specific exercise here that says evaluate the following integral, evaluate the following integral. That is the integral of, let us choose a specific one. Let us say this is tangent to the 6 of x, and this is secant to the power. Here, let us choose 4 of x dx just to illustrate the strategy here. We are looking for this question as combination of tangent secant, okay, where the secant has an even power. So this one is even. Okay, fine. The strategy say that if to integrate this, the only thing you need to do to start with as a classical way to move, this is tangent to the 6 of x, then you can write this one as what? Secant squared of x, and you need to save secant squared of x for the substitution you will do. So what I'm doing here, I'm just separating secant square, shooting for rewriting this in terms of tangent. Can we do that? The answer is yes, by using the help of this identity here. Okay, fine. So what is next then? After this separation of secant square, then you need to do the following. You have here tangent to the power 6. Tangent to the power 6 of x. Fine. What about secant squared here? Secant squared here will be 1 plus tangent squared of x. And we are saving secant squared of x dx for the substitution we will do. You can see now we have function of tangent multiplied by secant square. So it is f of tangent multiplied by the derivative of tangent. Okay, so what should we do? We will let u equal to tangent of x, and du will be what? It will be secant squared of x what? Dx. Fine, interesting. Let us look for the new shape of the integral. This implies our integral I is equal to, our integral I, if you allow me, I call all of this I is equal to this. So our integral I will be, this will be u to the 6 multiplied by plus u squared, and that is what? That is only du, secant squared dx. Fine, interesting. Just look at the new shape here. It is u to the 6 plus u to the 8 du. As simple as this. We are converting a trigonometric integral into simple integral. This is polynomial case. So what do we have here is just u to the 7 over 7 plus u to the 9 over 9 plus what? Constant of integration. Okay? Substituting back for u, you get the final answer. What is u? U is what? We just make u equal to tangent, so that is 1 over 7 tangent to the power 7 of x plus 1 over 9 tangent to the power 9 of x plus a constant of integration c. So that is the way we need to treat this kind of or class of integrals. Whenever we have an even power of secant, the method will be working fine. The method will be working fine here. Next one, what happened if the tangent function has an odd power? What happened if the tangent function has an odd power? That will be done in the next case. What happened if the, let's call it part B, we have power of tangent is odd. The power of tangent is odd. Okay, fine. Let us go back to the combination we have. We have combination of tangent and secant. So this is tangent to the power m of x. And we have secant to the power n of x dx. In the first option, we have the secant has an even power. So we should to make tangent equal to u. So we are looking for secant squared. That's why we said we separate secant squared. In the second case here, where this is odd, our target to make secant equal to u. If we need to make secant equal to u, du will be what? It will be secant times tangent times dx. So what do you need to save now? We need to save one tangent, one secant. So that's what we will do. So how to treat this one now? I will save one secant function, one tangent function at the end, dx. Of course, I don't care about this. It could be even, odd, whatever it is. Rational, positive, negative, I don't care. What about this one here? If you separate from it one tangent of x, this is m, which is odd. M minus 1 will be what? M minus 1 will be even. And if it is even, then I can replace tangent squared of x to be what? Secant squared of x minus 1. Meaning, I can rewrite this in terms of secant. So I will end up with an integral that involves everything here in terms of what? Secant. It is function of secant of x. Okay? And then what is the derivative of secant? It is secant tangent. So the strategy is working fine because I will end up with the non-trigonometric integral. Let us see this. Let us see this in a concrete example. Let us see this one in a concrete example. Okay, fine. Let us take this specific exercise that says find the integral of, I will choose a tangent with an odd power of x. Secant, I don't care. Maybe I can write it 1/2 of x if you like, dx. 1/3 minus 1/2, whatever. In this case, we have tangent with odd power. The strategy says, if you need to integrate this one, the only thing you need to do to separate one secant, one tangent. Okay, fine. If I separate one tangent, that is easy. I can write this one as tangent squared of x. I can save one tangent to the end. I have here, I have secant to the power 1/2 of x. I need to separate tangent of x, but I need also secant of x. Do we have secant of x here? Yes. You can here always multiply by secant of x dx, but you need also to divide by what? Secant of x, so that they cancel each other here, right? So always I can save tangent secant. Sometimes I need to adjust by adding, multiplying and dividing. So what do you get here at the end? I have, look, I have tangent squared first. Let me simplify, then use the identity. I have secant to the power 1/2 divided by secant, that is secant to the power minus 1/2 of x. And I leave that one because I separated in purpose. So this is tangent secant of x dx. I separate this one because I am shooting to make u equal to what? Equal to secant. Fine. So I leave that one to the end. Now next, what is tangent squared? What is tangent squared? Tangent squared is secant squared minus 1. So what do we have here is secant squared of x minus 1, all of this multiplied by secant to the power minus 1/2 of x multiplied by the rest of the thing here. Tangent secant of x dx. I will not touch this one because my target now to make a substitution. What is that substitution? I will let u to be equal to secant of x. And this of course implies that du is secant of x tangent of x dx. The one I saved, the one I separated. So this implies the integral now is equal to, now let us look for the integral in terms of u. This will be u squared minus 1 multiplied by, this is u to the power minus 1/2, and that is nothing but du. Everything here is just du, and this is u to the power minus 1/2, this is u squared minus 1. You can see now we are converting a trigonometric integral into simple integral like this, where we can integrate easily. So this is equal to what? And this is the beauty of this kind of discussion we are making now. We have 2 minus 1/2, that is 3/2. Simplifying, this is u to the power minus 1/2, and we are integrating now with respect to u. So what is the final answer? Before we substitute back, this is u to the power, that is 5/2, 3/2 plus 2/2, multiplied by 2/5, minus, that will be u to the power 1/2, so this is minus 2 u to the power 1/2 plus constant of integration, and this is, now we need to substitute back for u. U is equal to secant, so that is 2/5, this is secant to the power 5/2 x minus 2, this is secant to the power 1/2 x plus constant of integration. Okay. So we did now two cases. Combination of sine cosine with the subcases we have, and we have combination of tangent secant with the subcases we have. We will see now more exercises how to integrate tangent is odd. Tangent is odd or secant is even. We'll see more exercise only about this case to make it more clear. Now let us see more examples. Before I go to the examples, I just recall and note these two formulas that are frequently used in integration. What is the integral of tangent? It is equal to ln absolute value of secant. How to prove this? It is simple one. You just, we have tangent is sine of x over cosine of x dx. Then what the only thing you need to do is just to let u equal to cosine of x. In that case, du will be equal to minus sine x dx, okay? And then you substitute here. So the integral will be the integral of, this is minus du over u, so minus du over u. That is equal to minus ln absolute value of u plus constant c. Of course, when you take the minus inside, so that is ln of absolute value of 1 over u plus constant c. What is u? U equal to cosine. What is 1 over cosine? That is secant. So this is the first one. So then, but usually we use it frequently, so we need to remember this one somehow. Integral of tangent is ln of absolute value of secant. What about the second one? The integral of secant is ln of secant plus tangent. That is a little bit tricky one, but it is also interesting. Let us see this. How to prove this? I have secant of x, isn't it? So what I will do, I will multiply and divide by secant of x plus tangent of x. That's the trick here. So this is secant of x plus tangent of x. Of course, I am integrating with respect to x. Now, if you multiply by this, what do you get? You get the following. You get, look here. This will give you secant squared of x plus secant of x tangent of x divided by secant of x plus tangent of x dx. Fine. Now, if we made this is equal to u, if you call this one u, what is du? The derivative of secant is secant tangent. The derivative of tangent is secant square. So the derivative of secant plus tangent is secant tangent plus secant square. So that is what? du over u, which is ln absolute value of u, and u is secant plus tangent. This is the way we get this result here. I will use these two results to solve the following two exercises. The first one of them is integral of tangent cubed. That's the first one. And the other one is the integral of secant cubed. So the question here says, find the integral of tangent cubed of x dx. I will solve this one in two different ways. I mean, two different representations only. At the end of the day, we get the same answer. You may have different forms, but both of them are correct. What is the first one? The first one here, I will apply the following strategy. I will say it is tangent cubed. So tangent cubed, I will write it as tangent squared of x multiplied by tangent of x dx. Fine. Then for tangent square, I will rewrite it as secant squared of x minus 1. Secant squared of x minus 1. Of course, this is multiplied by tangent of x dx. As I said, this is one way to do it. I will do it by another way. So, what do we have here? We have tangent of x multiplied by secant squared of x dx minus the integral of tangent of x dx. I'm distributing the multiplication over the subtraction here. Fine. Let's look for this integral here. And this is the beauty of integrals. Everybody will look at it from different angle. Maybe someone will say, okay, I consider this one as an even power of secant. Fine. Separate secant square and then write the rest in terms of tangent and integrate that. This is clearly, if you call this is equal to u, this will be du. So the final answer is u squared over 2. So that is tangent squared of x over 2 minus the integral of tangent, that is ln absolute value of secant of x plus constant c. This is correct. Someone else will say, no, I look at this as it is an odd power of tangent. We say, fine, what should we do if we have odd power of tangent? Then we ask him to separate this one. We separate here tangent of x, secant of x, and we just write here secant of x. And then we will make this is equal to u, and du will be what? Secant tangent. So the final answer will be secant squared over 2 minus ln of secant plus c. Or I will say another option here to move from this step. Or you can write it this way. You can write it as secant of x, tangent of x, secant of x dx minus the integral of tangent of x dx. This is another way to move from this step. So the final answer here will be, if this is u, and this will be du. So the final answer will be secant squared of x divided by 2 minus ln absolute value of secant of x plus c. And maybe someone will say, is this one true? Yes, it is true. But are they equivalent? Yes, they are equivalent. They differ only by constant. How to see that? You can see that easily from the identity that says 1 plus tangent squared of x equal to what? Secant square of x. So if you replace here secant square by 1 plus tangent square, what happened? It will be 1 plus tangent square over 2. So it is 1/2 plus 1/2 tangent squared. But the 1/2 we get extra here. We can add it to the constant. We get another constant. So we are getting exactly the same form we have here. This is one way to solve the exercise. Now let me say another way to solve it. I will say method 2 to solve this one. So let me call this one method 1 to move here. And another way to move, I will not say it is a different method, but it is different way to move, different path to reach the final answer only. So how to move then? Someone from the beginning will say, we discussed the case if the tangent is odd. And since we discussed this one, let us use it. Let's use the methodology we did. Okay, fine. So in the methodology we say, if you have an odd power of tangent, the only thing you need to do to separate one tangent, one secant. Fine. If you separate one tangent, this will be tangent squared of x. Tangent of x, you don't have secant, so we need to multiply by secant and divide by secant. So I multiply and divide by this. So everything divided by what? Secant of x dx. Fine. You are trying to save this one. You need to save it to call it du later. So we need to play with the tangent square. Tangent square should be written in terms of secant square. So what do we get then? It will be the following. It will be, this implies our integral is equal to the integral of, look, tangent square is secant squared of x minus 1 all over secant of x. Okay? And that is multiplied by tangent of x, secant of x dx. Fine, interesting. Let's look at it here. Secant square over secant, that is secant of x minus 1 over secant of x. Everything here multiplied by tangent of x, secant of x dx. Now, if you call u, let u equal to secant of x, this implies du is equal to what? What is the derivative of secant? That is secant of x tangent of x dx. The differential of u is secant of x tangent of x dx, which is the thing appearing here. So our integral then will be, our integral is the integral of u minus 1 over u, that is du. What is the answer for this? This will be u squared over 2 minus ln absolute value of u plus constant c. If you replace back u by secant, what you get here is secant squared of x over 2 minus ln absolute value of secant of x plus constant c. And you can compare this one with one of these answers we get at the end. This is exactly the same. So any way you move, you reach the same answer. Maybe different form, yes, but all correct paths will lead you to the correct answer. The last exercise I have for you is about secant cubed, where this identity will be used. Before I go to that exercise, I bring your attention to the following. Now, what happened if we have a question like this? Combination of cotangent of x to the power m cosecant of x to the power n of x dx. And let us take a specific exercise before we go to the last exercise. Fine. Just bring your attention here. What should we do if we have cotangent cosecant? The answer, do the same exactly as the cases for secant tangent. Meaning, if you have the power of cosecant is even, what you need to save is, yes, you need to save cosecant squared. If the power of cotangent is odd, what do you need to do? You separate one cotangent, one cosecant, and the argument will be exactly the same as what we have done for the previous case. I'll give you an example here before I go to the last exercise. I promise. Now, let us see this nice exercise about combination of cotangent, cosecant, and we will see this one goes parallel to the cases we have for secant and tangent. So what do we have here is this. I put something like, if you like, e to the x. I put something like here, cotangent to the power, okay, 3 of e to the x. I put here cosecant to the power, let us say 5 of e to the x dx. So we have combination of cotangent, cosecant. I put e to the x in purpose to also show you that sometimes we need to make a substitution before we go to discuss the cases. So what should I do here? First, I will make a substitution. U equal to e to the power x. What will be du? Du will be e to the power x what? Dx. Fine. So the integral we have is equal to, e to the x dx, that is du. So we have cotangent cubed of u cosecant to the power 5 of u, and this is what? d, which is e to the x dx. Now what case we have here? Cotangent has an odd power. This is odd. So what you need to do the same as the case for tangent. In the case of tangent, we separated, or we usually separate tangent, secant. Here, what should we do? We will separate cotangent, cosecant. So what do we have here is the following. It will be cotangent, this is cotangent, it will be cotangent squared of u, secant to the power 4 of u, okay, this is 4. What do we have here is just cotangent of u, cosecant of u, du. I save this one to the end because I need to make cosecant equal to something else, w for example, and this will be dw. So what is next then? After separating one cosecant, this is not secant, this is, this should supposed to be, I just miswriting this, it is cosecant, sorry for this. Cosecant to the power 5 of u du. So again, this is what? This is cosecant to the power 4 of u. I separated one cosecant, one cotangent. I need to rewrite cotangent in terms of cosecants. That is, cotangent square is cosecant squared of x minus 1. I have here cosecant to the power 4 of u. Again, this is u. I'm using here u. And I am saving this, which is cotangent of u, cosecant of u, and du. Okay, fine. What should we do now? We make a substitution that is cosecant of u, for example, equal to w, and we'll see what will happen to the integral. So what I will do now, I will let w equal to cosecant of u. So what is dw? It will be minus cosecant of u, cotangent of u, du. Okay, fine. I have cotangent, cosecant, so I'm left only with the minus sign. So this implies our integral will be minus sine integral of, that is, w squared minus 1 times w to the power 4 times dw. Because du is minus cosecant of u, cotangent of u, du is equal to dw. So cosecant, cotangent with a minus sign will be equal to what? Which will be equal to dw. Fine. Now let us do the rest of the calculation now. We have here minus integration of w to the power 6 minus w to the power 4, and this is dw. So what is the final answer is minus, I open this as w to the power 7 over 7. I integrate minus w to the power 5 over 5 plus a constant of integration. Finally, I need to substitute back for w, which is cosecant of u, and then I substitute for u by e to the x. So at the end of the day, I get cosecant to the power 7 of e to the x. I'm substituting back all over 7 minus, this is cosecant to the power 5 of e to the x all over 5, and all of this plus constant of integration. So I just bring your attention that all the cases we did for tangent secant is also applicable for cotangent and cosecant. Now let us see a nice application for the identity I wrote there, the integral of secant of x. Now let us summarize before we go to solve the next exercise, which is the last exercise we have in this talk, that says find the following integral, that is secant cubed of x dx. I summarize the cases we did. We have even power of sine, even power of cosine. We have odd power of sine, odd power of cosine, we have even power of secant, even power of cosecant, if we have combination of cosecant, cotangent, then we have odd power of tangent, odd power of cotangent if we have these kind of combinations. Now, if we have different cases, what should we do? For example, if we have the tangent has an even power and the cosecant has an odd power. Similarly, if we have other cases than what we have discussed, I will say each question you need to think about it separately. Each question will have different idea. I mean, there is no general scheme to be followed. An example of that is this. Integral of secant cubed. Yes, if we had secant squared, that is easy to be calculated. If we have even power of secant, that is easy to be calculated because we have a clear strategy for it. How to integrate secant cube? This is a nice question that will combine the previous skill we learned, integration by part, together with trigonometric integrals. Let us see this. Okay. Let me call this as I, because I need it later. I will call it I. What I will do here, because I don't have a clear way to move, so I'll try to use integration by part. How to do that? I will call this one secant of x, secant squared of x dx. You see the trick here. I decompose it into two things. Something I can integrate easily, and something, I mean, I have the integral, but I may choose it to be u, and I can choose this one to be dv. So what I will do integration by part. So I will choose my u to be secant of x. I will choose my dv to be secant squared of x dx. Fine. If this is u, what will be du? What is the differential du? It is secant of x multiplied by tangent of x dx. And what will be v? The integral of secant squared, that is tangent of x. Fine. If we are using integration by part, look here. This integral I will be equal to uv, that is secant of x, tangent of x, minus the integral of v du. v du, that will give me secant of x, tangent squared of x dx. Interesting. What is the benefit now? We end up another integral, which is not one of the cases we did. It is neither odd power of tangent, neither even power of secant. But now this is very interesting. Look here. What is tangent squared? What is this equal to? This is equal to what? Secant squared of x minus 1. Let us try to substitute for tangent squared by secant squared minus 1 and see what will be gained. I will try to write it here because I need that formula. I need to keep it in front of you and see what will be gained after replacing tangent squared by secant squared minus 1. Interesting case you will have now. Look. You have your I, your integral is, according to the integration by part formula, we have secant of x, tangent of x, minus integral of, look. If you replace tangent squared by secant squared minus 1, and you multiply by secant, you get secant by secant squared, that is secant cubed. So what do we get here is minus secant cubed of x dx. Then, look, you have secant squared minus 1 times secant, so that will give you minus secant with a minus sign. That will give me plus the integral of secant of x dx. You see now the beauty of this formula. But take care of this. What is this? Integral of secant cubed. What we have start with. Integral of secant cubed, which is I called it I. So this is nothing but this one is I. What I will do, I will take it to the other side. So what do we get here? I get 2i is equal to secant of x, tangent of x, plus the integral of secant. But what is the integral of secant? Integral of secant is ln secant plus tangent absolute value. So that is plus ln of absolute value secant of x plus tangent of x. Okay, fine, we are at the end. So what is our integral now? Our integral is 1/2 times this. So 1/2 times Okay, I have secant of x, I have tangent of x, plus ln absolute value of secant of x plus tangent of x. We succeeded to get one antiderivative, to get all antiderivatives. Don't forget, we need to add constant of integration. These are sample of trigonometric integrals. We have different cases. If you need to succeed here, you need to make things clear. You need to classify them with the cases we did. Then you have a general way to move to get the final answer. That's it for trigonometric integrals.